So thank you to all the organizers for inviting me to describe Molecfit, which I hope that I can convince you is a quite general tool to correct for telluric absorption lines. So a number of people have contributed to its still continuing development, and I would like to take the opportunity here to thank them all. So indeed, the tool found its origin as an ideal code. H2O when we had no way to measure the amount of water vapor except by using Visier itself. The method was then used on Quires a bit later, and you would notice here that we actually use the emission lines. We tried with additional molecules, and it appears to work quite well. So it was deemed to be important enough by the ISO management that it should be transformed into an ISO-supported tool, and that was what the contribution from Austria as its in-kind contribution when the country joined ISO. And further developments are taking place as we speak to make the tool easily integrable with pipelines. The tool can be retrieved by clicking on this URL where all the ISO pipelines are located. And I give here the references to the two papers. I will not talk about other tools such as Tapas or Telfit, but I encourage you to look into the paper by Soda and Ulmamol, who compare Molecfit and these tools in terms of performances. So here's the plan of my talk. I will briefly describe the telluric transmission spectrum. I will see what are needed in synthetic spectra in order to be able to provide correct telluric absorption spectra and the corresponding Molecfit components. I will give some examples. And then I would invite you to go and maybe we can aim at having a blind telluric correction in the future. And I will end by a few final comments. So let's go to the telluric transmission spectrum. As the Earth is full of molecules, all these molecules leave traces in the spectra of our astronomical targets. In the visible, we have some ozone bands, and we have water vapor and oxygen. And the amount of water vapor, the water vapor lines increase as we go to the red. Between 1 and 2.5 microns, we start to have lines from carbon dioxide, from methane, and a bit of N2O. And as we go to the thermal infrared, then we have additional lines like from OCS, from CO, again from ozone, and as we go to more than to the Q band, then we are again just dominated by water vapor. Now, the standard method to correct for telluric lines is to observe a telluric standard star, which is typically a spectrum without much intrinsic features, so type of B0 to B9. And we should observe such a spectrum, such a star as close as possible in air mass and in time. Why as close as possible in time is that a lot of lines are produced by water vapor, and water vapor is quite variable both in time and in location in the sky. And why in air mass is that we have a number of lines which are in different parts of the curve of growth, and therefore they behave differently from with air mass. They are not linear with air mass. Not all of them are linear with air mass. The new method states that we should divide the sine spectrum by the telluric star spectrum, and of course all this is as a cost in observing time. In a typical night, one can easily spend 10% of the time just observing telluric standard star, and we can spend even much more in the case of a white star. And unfortunately, in some cases, it may just not be possible. Weather gets bad, one has to close the dome, or maybe there is a technical problem that occurs before the telluric star observed. In other cases, if people are interested in using data from the archive, then one can face the problem that the scientific goal is not the same for the person trying to do the study using archival data compared to the person who prepared the observations, and the kind of Telluric standard star observed is not necessarily the best one in all cases. So let's see if we can have a good synthetic spectra. So this Molecfit is not the first tool to aim to try to get a synthetic spectra. And basically, we need to have a number of items quite well known. So we need to understand properly the formation of atmospheric lines. We need to have a good knowledge of the molecular line parameters. Then we need to have the right temperature and pressure for each atmospheric layer and the right molecular abundance for each atmospheric layer. And that's where these 2 points where Molecfit is particularly new. And then the final item is to have a good knowledge of the line spread function. So regarding the formation of atmospheric lines, well, there are now quite a number of radiative transfer models that have been developed by our atmospheric scientists. We need to have a line-by-line radiative transfer model that include pressure shift components and simulate the formation of lines using void profile for each atomic layer, and eventually accounting for line coupling or continuum. With the prototype, with the ideal prototype, we use the reference forward model by Anududia, and now Molecfit is using more the LBL RTM. The second item is to use a good set of molecular line parameters, and now really the standard is using ITRAN, which is regularly updated. In the case of Molecfit, it is done through the EER database, which is also regularly updated. And this database has included 53 molecules and absorption cross-sections for many more. Regarding the temperature and the pressure of each atmospheric layer, so that's what we call atmospheric profiles, there are quite standard profiles for the temperature and pressure above 25 kilometers. What Molecfit uses for between 0 and 25 kilometers is our so-called GDAS profile. So the profiles that obtained from a meteorological server at the time and location of the observation. So Molecfit goes through your FITS header, or eventually some ASCII parameter file, will pick up the location of the observations with the date and time of the observation, and will go and retrieve the corresponding GDAS profile. Molecfit will also actually use the temperature and the pressure as provided by any weather station at the observatory in Paranal, typically, or Nasir, and will slightly modify the values for the time of the observation. And why this is important, here are two figures to show this, showing that if there is a small 1 degree difference in the measurement of the ground pressure, we can in some cases already have several % differences in the ratio between the transmission spectra. And similar aspect can be seen if we have a difference in the ground pressure. Another component is, of course, the amount of the abundance of each molecule in each layer of the atmosphere, so exactly the volume mixing ratio, is typically provided by an atmospheric profile. In the case of Molecfit, we use the GDAS profile, but for the other molecules, we have typical profiles. But usually these values are not accurate enough, and what Molecfit does is to be able is changing the values for all the layers by a fixed factor. The reason for this fit is sometimes not really clear. Actually, it may be caused by inaccurate values of the temperature or pressure profiles. Just to illustrate this, here is on the left an atmospheric profile of the abundance of water vapor that have the same total precipitable water vapor, so we have 2 millimeters. The black line shows no water vapor at the altitude of the observatory, while the red one shows that most of the water vapor at the observatory altitude. And you can see how much the corresponding spectra will differ. The final components of Molecfit is really the line spread function, which can be either analytical, and then we have a choice of analytical functions, or can be provided by the user, either as one profile for all the pixels or one profile for each pixel of the input spectrum. Well, I said final, but it's not actually final. We have also we need to have a good wavelength calibration to make this fit. So Molecfit actually has the possibility to use the Telluric lines themselves in order to fit polynomial coefficients to improve the wavelength calibrations. And in order to do a good fit, one also need to basically make a good representations of the local continuum. But we don't need to fit the whole spectrum. We only need to have the fit over some inclusion regions that include some of the lines caused by the molecules that we want to understand. So as a summary, Molecfit currently has a library called Telluric Core, which can be used now in all instruments pipelines, or we have 3 standalone recipes. In both cases, we have 3 steps, one which is a modeling of the spectrum in the inclusion regions, which provide a number of best fit parameters. A second step, which is the caltrans, which calculate the transmission spectrum for the complete spectral range. And the third recipe, which use this transmission spectrum to correct the list of spectra, taking into account their mass differences. So in summary, what are the parameters to fit? Well, the parameters that are related to the instrument. So basically the coefficients of the polynomial representing the wavelength calibration, and the parameters characterizing the line spread function. We have parameters representing the atmosphere, so that's relative abundance for each relevant molecule, and parameters related to the target spectrum, which is basically the coefficients of that represents the continuum. And I summarize here the number of parameters. It's usually at least 1, often more than 3, and can be quite a large number in the worst cases. So let's have some examples. Here is a cryo-array spectrum, so basically 100,000 spectral resolution. In a spectral region, when we have a large amount of a large line caused by water vapor with a number of lines either caused by methane or ozone. The spectrum itself is in black. Overplotted is the spectrum of a Telluric standard star in green, and in red is a spectrum of produced by Molecfit. And you can see that they are really very, very close to each other. If we make the comparison, if we divide the spectrum of the object by the Telluric or by the synthetic, here is what it looks like. Of course, we have regions where the flux is close to 0, so divided 0 by 0, we have basically no signal. But apart of that, we can see that the method is working really well. Here we have an example with a shooter. Here, the spectrum of a shooter was fitted in the areas marked in yellow, and then the whole spectrum was calculated by Molecfit, and you can see in red the corrected spectrum. I'll skip this. We can see also with CMOS. CMOS is a 24 IFU feeding medium resolution spectrographs. Here the yellow areas shows the region used for the fitting. Some bad pixels have been removed. You can see here in red the corrected spectrum. The same transmission spectrum was then used on another object, and you can see another corrected spectrum on the top. Here is an example with Vizier, so it's a spectrum obtained by Mario van den Akker. On the bottom, you see in black the spectrum of HD 104327. In red, you can see the fit obtained by Molecfit. The corrected spectrum appears here. Of course, we have problems exactly at the core of the lines, but this is somewhat better than the correction made by using the Telluric standard star, which itself shows some photostraight lines. So, Molecfit is actually used quite a lot by people using ARPS, Espresso, Carmenes, people looking for exoplanets. Indeed, Romain Allard in 2017 show in this spectra, so we have two spectra of stars, actually much larger number of spectra, because we can see the differences because of air mass. He was able to correct the Telluric absorption and the water vapor lines extremely precisely. So you can see the division of the spectrum by the fitted spectrum by Molecfit. And he reached this conclusion that the 1 sigma precision of 20 parts per million from the transmission spectrum demonstrate that space light sensitivity can be achieved from the ground, even for a molecule that is a strong Telluric absorber. So basically, we have the VLT, or the 3.6 meter flying above the atmosphere. So can we go further? I mean, we're making a lot of fits. Can we try to make a bold step and towards blind Telluric line corrections? So can we reduce the number of parameters to fit, and can we improve the profiles for temperature and pressure? So I've shown these slides earlier, right? What are the parameters to fit? Now, the first two sets of parameters are related to the instruments. Now, if we have a good external calibrations for the wavelength calibration, so if our spectrum is really well calibrated, we will not have to determine these parameters. If we have an AFU, or if we have a fully illuminated slit, or if we know the image quality, then we probably don't need to characterize the line spread function itself. If for some way we manage to get the abundance for each relevant molecule, for example, using a radiometer to determine the water vapor, or through maybe dedicated calibrations in the case of molecules that vary slowly in abundances, then we don't have to fit these parameters. So if we don't have these parameters to fit, then actually we don't need to fit the continuum itself. And in this case, we can indeed to have basically a transmission spectrum obtained for each observation. So is this realistic? Among the most important molecules up to 2.5 microns, well, we have oxygen, which is very stable, water vapor, which is extremely variable, but here we can have a dedicated radiometer. In the following slides, I will show some findings for methane and CO2, which show seasonal variations and general increase. And we need to go for the other molecules. So as William Yan has mentioned, we had the first radiometer installed in 2011. And since this is quite, I mean, show really a good potential. And in order to go to the next step, to provide redundancy, we have actually installed a second radiometer last year. So these radiometers provide an all-sky view of the amount of water vapor. So and provides also temperature and humidity profiles above the observatory. And since a few weeks, we now have these humidity profiles available in the ESM databases. These graphs shows a comparison of the radiometer profile in humidity in blue between the GDAS and the radiometer, both for humidity and for temperature. And you see that there are indeed some systematic differences. Using the ipsometric iteration, we can then derive the pressure profile, and these are the requirements for Molecfit. Using this, this is a spectrum of UVS. So you can see in black, all these lines are actually water vapor lines. And using just the full Richter maximum of one line and the information provided by the radiometer, we can get this corrected spectrum there. We can repeat this in the thermal infrared. If you go to 5 microns, here we have, again, the black line, the spectrum from a standard star. Using the radiometer, just the amount of water vapor fixed at 2.9 millimeter provided by the radiometer. I show here in red the model, and the division is shown in green. And of course, looks like it's really good. We can do the same for CO2. So Wolfgang Kausch has already shown this a few years ago, that we can reproduce the increase of CO2 in the atmosphere. So here are some lines, some CO2 bands obtained with a shooter. The spectrum has been fitted, except for the regions in the gray area, which shows regularly some problems, some data problems. And you can see in green the corrected spectrum, and here the difference between the spectrum and the model. Here again, the values for water vapor, there are some water vapor lines in this area, has been obtained from the radiometer. And you can see that we reach 0.5% in the amount of CO2. If we do this over a few years, we can see indeed that there is an increase in the amount of CO2 over the years. And for our purposes, we can see that it looks like that regular observations of CO2 is probably enough to provide, let's say, that we can use with the constant value, or at least regularly increasing value of CO2. It's the same for methane. So in black, we have the spectrum. In red, we have the model. And we have some water vapor lines also that's been provided with the amount provided by the radiometer. And we can see again here some small increase of methane over the years, but the values during, let's say, a season or during several weeks seems to be quite constant. You need to do the same for the same kind of studies for other molecules. Here, maybe ozone might be the most variable one, but this is just ongoing. So let's go to final comments. So currently, there is a large amount of work being done in integrating Molecfit in the data reduction pipelines. This has been done for CMOS and will be done for UVS, FORCE, BZ, and GIRAFF in the first go, and other instruments in the second step. We will cautiously change the calibration plan for near-infrared or mid-infrared spectrograph at Paranal. With the plan that we don't need to observe Telluric stars systematically anymore. But we need to continue to have some measurements for all the molecules that we need to monitor. We need to build a database of abundances for each molecule so that Molecfit can go and actually pick the right value for the corresponding night of observations. And But in order to do all this, we need to understand and hopefully solve all the problems that we face. On the longer term, we have the ELT instruments like METIS, which, as part of the requirements, should avoid to make nighttime calibrations. So Molecfit should be able to provide a synthetic telluric line correction or if we can indeed show that abundances of molecules are reasonably stable. We need to identify possible problems with the molecular line parameters, and there we can work with the people at the Observatoire de Paris. And there is also the possibility to improve photometry, for example, with the group from Speculoos reach 1.5 millimagnitude in the IZ band by correcting their photometry using the amount of water vapor observed at parallel. I would like to, as always, when I make a presentation on Molecfit, to make a note of caution. The reason is it's not because we have a very good telluric line correction that we recover all the information. If we have a line falling exactly in the middle of your telluric line, so the information coming from your object will just not be there and cannot be recovered. This may be obvious when we work at high resolution, but it might be less obvious at low resolution. So this is a note of caution. It's really, really important to understand this. So thank you. I hope that I've convinced that Molecfit is indeed quite a general tool to correct for telluric absorption lines, and that we can aim at blind telluric correction if the wavelength calibration is really accurate, if we know the parameters of the line spread function, and if abundance of molecules other than water vapor is reasonably stable. Thank you.
All right, thank you, Alain. We are already past 9:30, but I think we have time for, let's try to do one quick comment and then a question. Number one, I believe Uli had a comment to give. I am asking to unmute you, so I should give you a prompt.
Yes. Well, Alain, excellent the work, and I'm super grateful. I just want to expand a bit on what you just said, the word of caution. I mean, I hope there are still people around who do actually filter photometry, because what Alain has shown now is important at all spectral resolutions, especially if you do filter photometry. So for example, if you think about the neon 2 line is in a very bad neighborhood, and if you blindly ignore the atmospheric spectrum, you actually may end up with a photometry that's completely scrambled by the internal velocity structure of the object you're looking at, because maybe, you know, you will get a modulation of the neon 2 signal, whether it is moved into the water vapor line or not. And in that sense, I recommend to everybody to, at least in the preparation phase, to look into the exposure time calculator, which has a similar tool, to be sure that you don't have a telluric interaction really with your ionic line, for example, that you're looking at. And you may actually also look in this tool because you can play a bit with the season of the year, and that may shift actually your line into a less contaminated region. So I just want a word of warning. In the infrared, observing with our atmosphere, any observation, even if it's filter photometry and microscopy, because involving done a lot for this. I appreciate that.
Yeah, thanks, Uli. I fully agree.
All right, thank you, Uli. We also have one question I think I'm going to try to do here from Warren Skidmore. Can you comment on the temperature profiles used in the models you get them from radiometer, and has any calibration against radiosondes been done?
Yes, this was done in 2011 when the first radiometer was installed, and there was a campaign of radiosondes. So that's the work from, in particular, Florian Kerber, who really pushed to have this. And in parallel, there is also radiosondes from the Antofagasta airport, so it's 100 kilometers away. But in general, I mean, this is the argument is extremely good. There is a paper by Florian Kerber that describes the comparison between the radiometer, the comparison with radiosondes, and actually measurements made with VISIR and VISIR, Cryo-ES, and I think a few others spectrograph. I don't remember which one.